Hi guys, BuildZoid here, and so today I want to do a bit of a clarification video on the voltage, like the degradation video I did. In that video I mentioned that, yeah, if you run a lower temperature, theoretically you can run a higher voltage. Because your current draw will stay the same, because your current draw scales from both temperature and current. So today we're going to try translate that into the real world. So let's say we have well, not really real world, but I'm going to give a more concrete example of what that would behave like. So let's say we have a CPU that's 95 degrees, 1.3 volts. Actually, you know what? I'm going to make it easy for myself. 1 volt, 100 amps. Yay! I'm making it easy for myself. So, and this CPU, let's just say, has a temperature, scaling factor for the current draw of minus 10%. Per 20-degree drop, right? So, what this means, if we go from 95 to 70, and this is like a relatively realistic number because I have that from experimental data on some CPU I tested like years and years and years ago. Okay, well, not that many years ago, but like a long time ago. And it is a kind of testing that I'd really like to do more. Like, I'd like to do that kind of testing more, but at the same time, it's just like it takes a lot of time and effort. And I don't think, like, the thing is, it produces some interesting results, but they're not very practical for what we're about to get into. So, you know, you get your 70-degree drop, and that means you can go from 1.1 volts to from 1 volt to 1.1 volts, and you're still going to get your 100 amps of current draw. Yay! So your degradation should mostly be the rate of degradation due to electromigration should basically still be the same because the temperature is 25 degrees lower. Now, here's the problem, okay? If you have let's say this right here is on an AIO, you know, and AIOs, they're not that great. A lot of them will run pretty warm water temperatures. So let's say the water gets like 35 degrees. You know, I could have just changed that from 1 volt 100 amps to 1 volt 200 amps, and then that AI we're throwing out the idea that this is going to be like super realistic. Okay, so AIO, you know, 35 degrees. Room temp equals 20 degrees, and we have a problem here. The cooling system necessary to get this lovely temperature drop right here, right, is not ambient. Because the AIO is at 35 degrees. So whatever it is that runs this right here at 70 degrees would have to be at a temperature of like 10. So if we go like custom water loop with a chiller, so H2O, 10 degrees. Right, 10 degrees water temperature. If you were on like the world's, like on a monster water cooling loop with like way too many radiators, H2O, well, actually, I should have just gone chilled. So chiller, you know, you can get 10-degree water temperature quite easy, right? Like custom H2O, this is a limit. Like you can't go below room temperature without using a chiller. And there's just no way around that. So this is stuck at like 20 degrees, which unfortunately means that, you know, 95 to like this drop right here means you don't get this lovely, like you don't get that full drop right there. You get like minus 6%. So, you know, on H2 on this, you might be able to run like 1.06 volts, except for the fact that there's also the concern that, you know, if you raise the voltage, your power consumption comes back up because, yeah, you're going to be 1.06 volts, 100 amps, but that's 106 watts, not 100 watts, right? Like this right here, this is 100 watts, but this right here is 106 watts. So your temperature is actually going to come back a little bit after the initial drop. So you probably are going to be limited to like 1.05 volts. So for a 15-degree temperature drop, you get a 50 millivolt voltage increase in terms of tolerance, which is just like great. On a lot of CPUs, that'll translate to like maybe 100 megahertz, maybe less, right? Like it's kind of the issue. This is why this is not very practical. So anyway, at this point, you might be like, might be okay. Now the thing is, if you have a chiller, right, you can just drop the water temperature more. So if like 10 degrees doesn't actually hold you at 70, you can just go like, okay, we're going to 7-degree water temperature, right? And it's like, cool, now we're pulling 110 watts and we're still maintaining our 70-degree CPU operating temperature. And let's say you want to run even more voltage into the CPU while still maintaining the same degradation rate. Well, from 70, you can try drop to 45 degrees. Do you want to know what that does to your water temperature? So now you're looking at a chiller, a big chiller, with like not water in the loop, which, fun fact, water is basically, outside of like very toxic chemicals that you really don't want to be running as a cooling system, water is the best coolant you can get because it has a very high thermal capacity, which means, because here's the thing, in a water loop, the conductivity of the water is kind of irrelevant. The whole point of the water in the water loop is that you can dump a lot of heat into the water and then transport the heat in that water very quickly by the use of pumps, right? That's why you have the pump. So the pump, like the water basically just acts as a storage medium. And the fact that water is not very thermally conductive, like here's the thing with thermal conductivity, right? Is like, if this is water, right? We just have a block of water and it's still, and we're going to pretend like it's not liquid water because liquid water has like convection currents in it. And we're just going to pretend that this is water with like liquid water conduction rates, but none of the currents, right? Let's say it's like a sponge soaked in water, right? So that the water can't move. Because if the water can move, then it kind of screws with it. But compared to like a metal, because metal particles, they don't move when they're conducting heat. Whereas like like if you put a fire here, you're actually going to get a convection current that like basically you have hot water rising and then it like cycles like that, and that's going to boost the thermal transfer rate a bit. But if we just have like water that doesn't do that, then yeah, if you have a big block of water, then it's going to take a long time before this side of the water gets hot. But the whole point of a water block and the microfins inside the water block is that there's very little water, right? Like, because that's the thing, is like in your CPU, you basically have a heat source, right? And then the water is just like jammed into this tiny little channel, and like basically the microfins are basically like, the whole point of microfins is that you don't need to worry about the conductivity of the liquid that you're using to cool, because there's not a lot of it for the heat to have to like the heat doesn't have to travel through a lot of water. It just has to make the jump from the fin to the water, right? Like to the surface of the, like the first couple particles of water, like the little water that's jammed between the fins. So, you know, that's kind of the thing. So the conductivity of the water is basically irrelevant. The main priority is the fact that water has an insane thermal capacity of like 4,200 joules per kilogram. Which is like, this is great. This is pretty great. This means that to change the per degree. Actually per degree Kelvin. We could use Celsius. Like they're the same like scale in terms of whatever. But anyway, so basically this means you need, like, if you want to change the temperature of a kilogram of water or 1 liter of water in by 1 degree in 1 second, you need 4,200 watts of power to do that. Okay, like you need a hell of a lot of power to do that, which is why water is so which is why water is great for water cooling, because there's very few liquids that won't kill you that have this much thermal capacity. And if you're chilling water and you're going sub-zero, you're going to be running steadily more and more like glycol or some kind of like alcohol as an additive, right? And the issue with all of those is that they don't have as much thermal capacity as the water. So, you know, if you, like, I can't remember any alcohol thermal capacities off the top of my head. So anyway, let's say you have a theoretical liquid that's like 2,000 joules per kilogram. Right, and per degree Kelvin, and you mix it 50-50 with the water. Well, now your thermal capacity is basically like, you know, the middle ground between these two, which is like, what, that's 3,100 joules per kilogram, right? like assuming that they both also have the same density to kilogram ratio and that kind of thing, because a lot of things are also going to be like lighter than water or heavier than water, and that just makes it really complicated. So we're just going to pretend that's not a concern, and we're just going to say, okay, you mix it, 50-50 per, actually, no, if you do it 50% by mass instead of 50% by volume, this will be accurate. But now your water is less efficient at transferring heat because it takes less of a temperature increase to takes less heat to increase the temperature of the water. And the whole idea behind the rate at which the heat can travel from the fins to the water jammed between the fins is entirely dependent on how much cooler the water is than the fins, right? So that's why you want a very high thermal capacity, because the bigger the temperature difference between the water and the fin of your water block, the faster the heat will jump from the fin into the water. There. I am so good at explaining this stuff. Actually, I did a great job of that. Like, considering, like, I actually, at one point I was considering dedicating an entire video to why, like, people need to stop looking for alternatives to water because water's great. Like, there's, like, one liquid I'm aware of that has, like, a significantly higher thermal capacity than water, and that's liquid ammonia, which is just, like, you don't want to cool anything with that. Though apparently it is used for cooling things in some industrial processes where it's like, I guess water just really wasn't an option there. Because otherwise, yeah, water is freaking awesome. It's got a huge thermal capacity. It's easy to pump around. It's not ridiculously viscous, or really high. Is it really high Yeah, I keep getting viscosity mixed up. So anyway, you get it. It's not really thick. Like, it's easy to pump around. So yeah, that's why everybody just keeps using water. Right? And the only thing you ever really do with water to try, like the only thing, like everything you add to water that isn't water is probably worsening the thermal performance. But most of the time it's done for like, oh, we don't want corrosion. You don't want things growing in the water, because if things start growing in the water, it gets really hard to pump it, right? So, there's other, like, that's what all the additives to water are for. There's literally no additive I'm aware of where it's like, oh, this actually adds performance. There's additives to raise the boiling point, right? To lower the freezing point, that kind of thing. There's nothing that's like, oh yeah, we want higher, you can't find a liquid that'll make water, because it's not about the thermal conductivity. It's about the thermal capacity. And there's just not that many liquids that have a higher thermal capacity than water. So anyway, so if you're on a chiller, you're actually going to need to drop your your not water temperature, like your coolant temperature, even lower, because your coolant gets steadily less and less effective as you drop the temperature that you're running the coolant at, because it's going to be less and less water, right? Like, actually, I've heard of a few people who ran like cooling loops that were literally just like acetone, just straight acetone. And it's just like, well, not as efficient at transferring heat as water, but you can't cool water down that much, right? Like that's the reason why at some point you transition to liquids like that, where it's just like, oh yeah, sure, it doesn't have the thermal capacity, but have fun trying to pump water at minus 50 degrees, right? Like because a lot of the additives that you can get for water that lower the freezing point, they thicken up. So ultimately you get like a really sludgy fluid that then is like, well, it's hard to pump. So at that point you may as well just go with way more, like you can just go with a fluid that doesn't freeze and is still very isn't as thick. And it's like, yeah, so the thermal capacity might be terrible at that point, but at least you can pump it, right? Anyway, so this is why this gets really impractical really fast. So another 25 degree drop. It is worth noting that this improvement gets smaller as your temperature gets lower. So while going from 95 to 70 might give you a 10% drop, going from 70 to 45 will probably only give you like an 8% drop. And this gets smaller and smaller as you keep going down. Anyway, minus 8%. But we're gonna keep this easy for me. So we're gonna keep going with 10% per 25 degrees, because this is not realistic at all at this point, and so we're just gonna throw all of those considerations out. So 1.1 volts. Now you can go like, oh, I can run 1.21 volts, except my water chiller temperature has to be like 7 degrees minus 25. That's gonna be 2 minus 18. You know what, to hell with it. Like, you're just going to go for like minus 20 degree water temperature so that you can run 1.21 volts. Like, Oh, and this is again like maybe, right? Maybe. Because again, your power consumption at this point is going to be 121 watts, right? Because you're still going to be pulling 100 amps. So this gets very impractical very fast. And this is like, because the thing is, a lot of people, as soon as they go like, oh, my new cooling system runs 10 degrees cooler, right? Their idea is to just crank up the voltage until they're back up at the thermal limit, right? Like right back up at 95 degrees. And then it's like, well, that's why you're getting degradation, because your current draw hasn't changed. Your voltage is higher. And like you need to maintain the lower temperature. You can't just go like, oh, I'm gonna lower my operating temperature by 5 degrees, so now I can run like 2% more voltage at 90, back up at 95. Like, no, you can't do that, because your current draw is going to go up, right? Like if we took this right here, right? If you run 1.1 volts at 95 degrees, it's going to be 110 amps. If you run 1.21 volts at 95 degrees, it's going to be 121 amps. That's the whole issue. So you need the temperature drop. And if you're at 100 and, if you're at 1.21 volts and you push your temperature back up to 70, right? Because your water chiller doesn't actually manage to do minus 20 degrees, then you're going to be pushing like 110 amps through your CPU. And you're going to be, like, the issue is, like, I really find it hard to believe that electromigration is that linear. So there must be some other effect that I'm not aware of, where it's like, yeah, if you increase the current draw by like 10 amps, then it's like noticeable degradation. Like there might be some internal hotspotting thing going on that really screws this over. So you might actually need an even bigger temperature drop than you initially think. Basically, this right here, I would be concerned that this probably isn't okay. But if you went down all the way to 45 and then ran 1.1 volts, right, you'd be getting 90 amps, and I would feel like, okay, this is probably pretty damn safe, right? Like 45 degrees, 1.1 volts, 90 amps, like you're pulling less current than, at 95 degrees. You're pulling less current. You're actually probably running around the same power consumption. The fun fact is, as you lower operating temperatures of CPUs, their frequency capabilities actually improve. Oh, right, that's the other factor. If you crank up the voltage and your frequency goes up, your current draw goes up with it. So also keep that in mind. This is all assuming that you maintain the same frequency. If you raise the frequency by 2%, that increases your current draw by basically 2%. So that's the other concern, is like, yeah, if, you can't if you raise your power, like if you raise your voltage by 10% and then you raise your frequency by 2%, so you go from like 5 gigahertz to 5.1 gigahertz, you are now, running 102 amps instead of just 100, which probably won't be an issue. Again, I don't know that, like, I don't have like proper test data where it's like, oh yeah, this is the rate of degradation under these operating conditions, and this is the rate of degradation under these operating conditions. Like, I don't have data for that. I do have data for, like, yeah, if you drop the temperature by X, you get a current draw reduction of Y, and if you raise the voltage by Z, or you raise the voltage by A, you get a current draw increase of A. And if you raise the frequency by B, you get a, power, like current draw increase of B as well. So I have data like that, but I don't have data for like how exactly that everything translates into straight up electromigration. That's the main issue. But anyway, so I would not be very confident about this, even though, like, yeah, but your temperatures are great. And like, no, I would not be too happy about that. But this right here, I'd be pretty happy with, except for the fact where it's like, yeah, find a 20-degree chiller, right? like minus 20-degree chiller. Because that's the whole issue. You need to be like way below room temperature to maintain like usefully lower temperatures on the CPU. And the other thing is, But the other thing I wanted to point out is at 45 degrees, your CPU should clock like way better than 95. Like that is such a massive temperature drop that, especially with like GPUs or something, there it's really noticeable because GPUs have really fine adjustments in frequency, right? You can add like 10 megahertz. But yeah, if you take a GPU from like 80 degrees down to 40 degrees, you can easily pick up like 50, 100 megahertz without even touching the voltage, right? So just the temperature drop alone will easily translate to, you know, a couple percentage points more clock speed. So this right here, let's say that's 5 gigahertz, right? This might be 5.1. Well, this here might do 5.3, but this already would do like 5, maybe would do already like 5.2, right? We're like, I'm assuming the scaling behavior that I don't think this matches any real world CPUs that accurately. But yeah, so, you know, you'd be giving up 100, like, you know, that extra voltage translates into, sure, another 100 megahertz, but it's just like, well, you could be a lot safer and just run less run less voltage, still have a bit much higher frequency than at 95, and pull less, like, going from 5 to 5.2, that's what, like 4%? So you'd still be under the 100 amp current draw, and you should be very, like, this should be very safe, right? But not practical, like, at all. So that's kind of the thing, is just like, yeah. So, and then of course, you know, if you're on liquid nitrogen, then you get like minus 190 degrees on the base of the LN2 pot, but the internal CPU temperature is probably somewhere like minus 50. If you're really heavy load, easily, well, actually, yeah, high current draw GPUs are like easily minus 50 to like internal silicon temperature, where it's like, yeah, you're not actually getting as much of a temperature drop as you were hoping for, because as you crank up the power consumption, the temperature delta between the cooling system and the thing you're cooling gets bigger and bigger and bigger, right? That's the other concern you run into. So anyway, this video is like 22 minutes long now. I think I've said everything I wanted to say. Yeah, I'm not sure I'm not sure this will go public though. I'm not very, like, this is so, like, here's the issue with this. I don't want anybody watching this video and going like, oh, this is true, because I don't know that this is true. I just know, like, the current scaling, yes, that's true. The voltage scaling, true, because again, I have experimental data proving that. The fact that you can go up in frequency if you just lower the operating temperature, also true. Like, that's been like, that's part of, like, if you run 1.6 volts on liquid nitrogen, it will clock way higher than 1.6 volts at ambient, and that's not up for discussion. That's just a fact, right? So, you know, like, all of the scaling factors, that I stand, like, the scaling behavior, I stand behind that. I do not stand behind saying this would be safe, because I have no idea. I would assume that it shouldn't cause any more electromigration than this, but don't take, I wouldn't trust my own advice there. So I would actually, like, I would not go and take my 10% decrease in current draw and just ram it into a 10% increase in operating voltage, because that just seems like a great way to get surprised in a year when it's like, why does it blue screen when I try to encode video? Or why does it blue screen when you try to, like, unzip a file or something, right? Anything big, like any multi-core high power consumption workload where it's like, after a year of running your CPU at, like, oh yeah, it runs like 10% cooler at 10% more voltage, and then after a year you're like, why is it not stable anymore? And it's like, well, probably because you degraded it, you know? And that's kind of the issue there. So, you know, it's nice that, like, this might very, like, for, I don't know for how many architectures this might be true, but definitely for some this is true. I would not use that to try, like, I would just still not take that into a direct, you know, voltage increase, because, yeah, I don't have experimental data that says, like, this is fine. And also, I don't know that you're, like, there's a good chance, like, the oxide breakdown doesn't scale as quickly as the electromigration stuff. So if the electromigration outpaces the oxide breakdown by a large enough amount, you might end up actually like with voltages that, okay, you're not, melting the wiring of your CPU away with current, but you are putting holes in your transistors. And that's really, like, that'll kill the CPU just as much, like, just as well as, having, like, electrons eroding all of the wiring. So, yeah, it's like, I would, like, basically, you need massive temperature drops before you can even start considering, like, hey, I'm going to raise the voltage a bit. Okay, like, I'd be very careful with this. Like, super... because the thing is, I actually, like, I degraded quite a few CPU. Well, okay, no. I degraded, like, one chip, and since then, I've just run with a... Because also, there's, like, the LLC issue, right? Like, I'm not sure how LLC would factor into all of this, but anyway, like, I remember degrading one pretty good chip. And I, like, the funny thing is, like, I primarily blow up memory controllers. Don't ask me how. It's actually, no. It's very simple. Memory controllers are way more fragile than cores. Like, cores generally, they degrade pretty gently. But, yeah, I've blown up memory controllers quite regularly. But the thing is, like... Yeah, I don't, like, I don't know how useful this is in the real world. But basically, yeah, if you have a crazy cooling system that keeps your CPU, like, like, the thing is, because if you run this, you're also going to need to have, like, a ton of insulation in your system, or you're going to also have to have, like, another chiller for your internal, like, if you thermally insulated your entire case, because I saw somebody do this where it was, like, that was a great idea on their part. Basically, what they did is they had a water chiller, and instead of, like, trying to insulate the motherboard or anything like that, they just had the water chiller chill the inside of the case as well, right? So basically, the internal case temperature was, like, 10 degrees, and the water temperature was 10 degrees, and it's like, well, you're not going to get condensation if the ambient air temperature is the same inside, like, if the temperature inside the system is the same as the temperature of the water, then it's like, yeah, you'll be fine. So, if you want to run a minus 20 degree water chiller, you might want to thermally insulate your entire case, and then run your minus 20 degree, like, run the internals of the system at, like, -5, right? Like, the air temperature at -5 and the water at -20. Now, you might have a static electricity buildup hazard doing that. So, be very, like, have everything very well grounded, I guess, if you're going to mess around with something like that. Also, it's worth noting that some memory chips get very upset if you get them too cold. Like, at -20 degrees is cold enough that certain memory chips will start getting very unstable. So, yeah. Anyway, oh boy, I just made this video even longer. It's like, this is, like, there. Hopefully, this is useful, and it stops you from blowing your CPU up because you see, oh, I make cooling systems 5 degrees better. Let's raise the voltage. No. Like, don't. Like, 5 degrees cooler is not cooler enough. Like, 30, sure. At 30 degrees, you might start being allowed to consider, like, yeah, I can bump up the voltage a bit. A bit, like, not a lot, a bit. Okay, like 10, 20, maybe 50 millivolts. But otherwise, yeah, it's just like that, and even that, like, even 50 millivolts, like, I don't trust that. I really don't trust that. It's just like, there's no good long-term, like, test data for this stuff. So yeah, it's like, within my understanding, it would make sense that it would behave kind of like that. But anyway, so I'll just end the video here because this is not going anywhere at this point. And I think I've said everything I have to say on the topic. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. And if you'd like to support what I do here with Actually Hardcore Overclocking, I have a Patreon where you can support me directly, which will not go into testing this kind of thing because I'd like, well, I'd be interested in finding out if this is actually true. I'm not very interested in being the one testing this. This is really boring testing. Anyway, so yeah, I have a Patreon. You can support me directly there. And then there's also the AHOC Teespring store where there's shirts, stickers, posters, the usual YouTuber merch. And you can support me by buying some of that stuff. And there's a link to that down in the description below as well. So yeah, that's it for the video. Thanks for watching and goodbye. Don't actually try to apply any of what you've seen in real world applications, because this is probably not accounting for all of the variables that there are, because I'm not aware of some of them. So yeah, that's it. Thanks for watching. Goodbye.